Hello, everyone. Welcome to my presentation. Today, I'm going to talk about vCacheShare, which is joint work involving my summer internship mentor, Li Zhou, Yutam Chandani, and who were all with VMware during the time, and my PhD advisor, Xiaosong Ma. Virtualization has been widely used in data centers for efficient resource consolidation, such as CPU, memory, storage, and network. Remote shared storage provide richer management features like snapshot, clones, etc. It also facilitates hypervisor events such as VMware's flagship vMotion product. There are more and more hypervisors begin to use server flash cache or SFC to accelerate the I/O performance as a host-side cache tier, which moves hot frequent access data to flashcards from network-attached disk arrays. SFC is able to accelerate I/O performance of the hosted virtual machines. It increases the VM to server consolidation ratio, which is a very important performance metric for hypervisor. For servers which share the same storage device, SFC is also able to reduce the workload on those servers, and it reduces the I/O contention from those servers. A new problem comes up when SFC is in the storage picture. The hypervisor needs to divide the SFC space to its virtual machines, just like other shared resources. But unlike CPU and memory, SFC is transparent to virtual machines. There were mainly two SFC management policies when vCacheShare was designed. The first one is called static space allocation, which allocate static fixed SFC space to virtual machines, which cannot be changed until the virtual machine is shut down and restarted. The other common policy is what we call globally shared. All the virtual machines share the same SFC space. With cache eviction policies such as LRU or its variants. NetApp Mercury use such cache policy, and Facebook Flash Cache, vCache, and Extreme Cache use a static allocation policy. The two approach apparently both have disadvantages. Static space partitioning cannot adapt, while globally shared policy is vulnerable for problems such as cache pollution. So we present vCacheShare, an automated SFC management framework. It dynamically resizes the cache allocation to virtual machines based on its observation of workload locality as well as system events. vCacheShare combines both long-term and short-term workload locality for efficient cache resizing. So vCacheShare strives to provide a hypervisor and optimized SFC allocation framework in an automated and continuous way. It takes into consider several different factors. First, a VM priority, which is defined by sysadmin based on the service level agreement of virtual machines. Following that, workload locality and I/O characteristics are also considered by vCacheShare. Also, the performance of backend device is considered by vCacheShare. Intuitively, VMs with slower device needs more cache space. Finally, designed for ESX, vCacheShare has to work seamlessly with virtualization management events, such as VM power on, power off, VM suspend, resume. vCacheShare allocation has to adapt accordingly to these management events. For example, when one virtual machine is shut off, vCacheShare stops the allocation automatically. Here's an overview of vCacheShare. vCacheShare performs dynamic cache partitioning based on continuous access history monitoring and analysis for each VM. It also adopts a cache utility model to answer the question, how useful is more cache size to a particular workload or VM. The cache utility model considers two metrics simultaneously. It models the familiar hit ratio, which is very common we use to model the locality of workload. But it also considers another metric, what we call hit ratio. It reflects long-term. It reflects short-term locality of the workload. So here's a diagram of vCacheShare. vCacheShare is designed to span both kernel and user space within the hypervisor to manage shared SFC space between multiple VMs and backend storage device, which are usually network-attached shared physical hardware. It contains multiple components. The cache module manages the flash cache. The monitor captures workload I/O history, which is fed periodically to analyzer for further analysis. Following that is optimizer. It optimizes the cache allocation based on the result from analyzer. And finally, actuator combines the result and work with cache module to do the reallocation for the virtual machines. Now I'll zoom into the cache module and discuss several vCacheShare decision design choices. First, cache policy. Write back or write through. We chose a modified write back. We chose a modified write through. The I/O operation we received has already been filtered by guest virtual machines memory buffer cache. So the read after write ratio has been reduced a lot. Considering the complexity of write back cache plus the limited lifetime of flash writes, we use a modified write through cache for our design. Secondly, at which level do we build our cache? One prior solution was to assign each VM a virtual file, but that doesn't work well with dynamic cache sizing. We chose to build a block-level cache ourselves and work out several engineering challenges to make the cache VM aware. Finally, we chose LRU as a cache replacement policy. Now our second component, the monitor. The monitor resides between VMs and SFC. It integrates, it intercepts I/O access to collect information useful for cache partitioning. Here we show an entry of collected trace. Such trace data are written to a circular buffer built across main memory and SSD special partition. Entries written to in-memory buffer are dumped asynchronously to the SSD part. And when the segment's full, it's automatically copied to the user space analyzer. With the workload we tested, such I/O tracing does not add in significant overhead. When I/O is intensive to the point where complete tracing is it's too expensive and not necessary, the vCacheShare monitor is also capable of sampling. Now we came to the third vCacheShare component, the analyzer. It processes the trace segments supplied by monitor. Based on each segment, it outputs two results. The first one is circular distribution. It's a cumulative distribution for reuse distance, which will be used by vCacheShare optimizer to calculate the hit ratio at a given cache size. Hit ratio is an important and familiar measurement for the locality behavior of a certain workload and has been used in many previous studies, say CPU cache for partitioning. However, we found hit ratio alone is not sufficient to capture the real cache, the cache locality, as it requires rather long-term monitoring and ignores information such as access speed. In this diagram, we show two VMs with exactly the same trace our VM1 get this access using 2 hours, while VM2 is using only 10 seconds. So to compensate for that, the vCacheShare analyzer collects a new metric, which we call reuse intensity, or RI. It measures how fast the data are revisited, which is very effective to allow vCacheShare to adapt to sudden locality bursts. For a given monitoring window, RI is established as a ratio between the total access volume and the access footprint over unit time. You can see this measurement is relatively coarse and cheap to obtain. Therefore, RI can be accessed more frequently using a smaller window size. Finally, we got to vCacheShare's optimizer. For each VM, it is able to calculate cache utility as a function of cache size. The utility is modeled as a product of several things: the backend device latency, L, the read ratio, RI, the estimated hit ratio at a given cache size, HC, and finally, the reuse intensity, RI. The alpha is used as another sysadmin controller tuning knob to vary the relative weight between HR and RI. In our experiments, alpha is actually set to 1. The optimization is then quite straightforward. We want to maximize the overall cache utility, which is the total cache utility of all VMs, weighted by their priority levels. Such optimization has to satisfy 2 constraints, though. First, the per VM allocation adds up to the total cache space. Second, for each VM, the allocation has to fall into a pre-configured range, again set by sysadmin. The problem is NP-hard, and we used an open source tool that performs simulate annealing for approximation. The result is then the new allocation for the next time period. Due to the time limit, we're not going to give much detail about the actuator which implements the new allocation. One thing we want to note is that lazy eviction is used to maximize the utilization of cached items. We have just described the main workflow of vCacheShare. A little side note about before we go through the results. So virtual computing environment today is highly complicated and dynamic. We designed and implemented vCacheShare to work with runtime VM management events as listed in this table. So in the next few slides, I will show some evaluation results we have. The prototype was implemented within VMware ESXi 5.0, consisting both kernel and user space code. For the evaluation, we use the listed hardware and VM configuration listed. So in this setup, we are conducting a micro benchmark evaluation. There are 2 VMs with equal priority accessing identical storage devices. The x-axis shows time, and y shows relative cache allocation in terms of percentage of the total cache space. We have 4 curves here. The hollow bullets are for VM1 and solid for VM2. We compare global LRU, GLRU with vCacheShare. GLRU is shown with square bullets and vCacheShare with triangles. The 2 VMs both run the same I/O workloads generated by iometer. Therefore, all curves behave pretty much the same at the beginning. As the cache warms up, we manipulated the benchmark profile to shrink VM1's profile at a certain time. The workload then converges again and manipulated again to replay the access trace of VM2. Therefore, we generated 2 artificial locality bursts for VM1 and 2, respectively. The square curves show GLRU allocations. You can see GLRU does adjust the allocation, but in a rather minor way. In contrast, vCacheShare, the triangle curves made such more significant adjustment. Globally shared policy actually allocates more space to workloads with higher I/O access rate instead of high data locality. As a result, we can check the difference this made in VM's I/O latency. compared to GLRU, vCacheShare is able to produce much more pronounced drop for VMs that experience locality bursts. But by allocating more cache space to it without producing significant performance degradation for the other VM. As a macro benchmark, we check whether vCacheShare helps to speed up VDI bootstorm. VDI, also known as virtual desktop infrastructure, is a typical virtualization use case with low IOPS but generate high load spikes. The graph shows latency change and the finishing time of different cache allocation strategies: no cache, static, GLRU, and vCacheShare. The bootstorm completion time varies a lot between them. Static is the fastest one, 72 seconds. vCacheShare finished 14 seconds, while GLRU with 242 seconds, and of course, the no cache is the last. Note that static allocation wins here at a certain cost. It gives unnecessary high cache allocation to those booting VMs. Here we show the latency of the iometer workload. With static, it stays high, while with vCacheShare, it only experiences a temporary performance degradation for the duration of the bootstorm, and afterwards returns to its normal latency, which is around only 17% of the latency level with static. So to summarize, vCacheShare proves that dynamic SFC partitioning is affordable and worthwhile. It alleviates the burden on administrators to predict the dynamic workload change. The overall cache utilization managed by vCacheShare proves to be better than the static and globally shared allocation policies. Secondly, long sampling window is desirable for accurate cache hit ratio estimation, but cause slower response. We remedy this problem with a newly introduced reuse intensity metric, which complements hit ratio estimation with short-term locality monitoring. So there's one future work we want to finish is the relationship between sampling window size and hit ratio estimation. This concludes my presentation. I would be happy to take any questions. Thank you.
Chang Li from Rutgers University. So in your methodology, you talk about sampling. I wonder if you need to do multiple sampling for different consolidation scenarios.
So in our test, we actually get all the traces. The sampling could be enabled if there are numerous traces which the CPU is not able to handle, and we're restricted by the kernel memory space. Does that answer your question?
No, I'm say you have multiple tenants. Sometimes you have 5 VM, 4 VMs. Does that affect your reuse distance CDF? It should, right?
We have a reuse distance CDF for each VM. So the number of VMs does not actually influence our result. So the model is for the cache utilities for each of the VM. So for example, you have 5 VMs. There are 5 models for the 5 different VMs. And it's not related to each other.
Okay, we'll take it.
Thank you.
Xiang from NJIT. Actually, I'm curious, how do you handle the context switches inside the VM? Because it's transparent to the virtual machine manager. So if there is I/O operation, there is a context switch inside the VM, right? So you have to switch the data matrix you collected.
What do you mean by context switch?
All application switches.
We actually don't care about the context switch because we are working from the storage angle. What we care is just the I/O access. So all the context switch has been taken care of by hypervisor itself. It's not the job of the storage component.
If there are application switches inside the virtual machine, your measurement will be updated accordingly, right? So actually, your measures the utility function for one application inside the virtual machine, and sometimes the application changes inside the virtual machine. So you have to update the utility function to reflect the changes.
The utility function is actually on the disk itself, not about the workload, because we have no knowledge of what kind of workloads is running inside the virtual machine. What we can see from hypervisor is the disk it accesses. So there might be different workloads working on the same virtual machine disks, and what we care is just the disk itself.
Okay.
Thanks, Peter.